Hello everyone. Then for this presentation, Hilbert Basis activation function for neural network presented by Souza de Courcy in laboratoire de mécanique in Sadoran, French. عبد الكريم المعتصم بروق طريق in Department of Mathematics Management, team of Applied Mathematics and Computer Science in Ouarzazate, Morocco, and Al-Rashid Illaya in Lerma Mohammadi School of Engineering in Rabat, Morocco. This work presented in the International Conference Uncertainties 2023 in Brazil. The introduction will talk about deep learning. Deep learning is a branch in machine learning that is a field in artificial intelligence. This method classified in supervised. The idea is common or inspired from human brain. There is a lot of architects for this technique, such as multi-layer perceptron, convolution neural network, CNN, and RNN, LSTM, generated plain text, for example, language automatic processing, and more. We start by the architect of neural network. For a simple example of Perceptron, where we have just one neuron here, and here is the input variables of that. Each variable input collects with this neuron by multiplying with parameter theta. Okay? Then pre-activation, the results is equal theta transposed time x. And after the activation, this value can be input of a function g for the output z. More specially, more explain, x can be a vector 1x1 to xm for each inputs in data set. We can use the vector. If we have the matrix, for example, the image, etc., we can be transfer it to the vector, for example. And the weighted parameter, that we can't find the optimization method, for example, it is also the vector theta 0, theta 1 to theta and transposits. Then we have here scalar products. It is the summation of the each components 1 to theta 0, the x1, theta 1, etc. Okay? After that, for this neuron, z equal g of e. For example of sample active function, threshold row, for example, if we have a row greater or equal than e, then the value of g row of e equals 0, else equal 1. For example, here products x, theta transposite x, we find equal 0.5 e. Then if we apply this function g row of 0.5 with row equals 0, since 0.5 greater than 0, then we have 1. Then for the correction of weighted theta star, we can suppose that we have a space, hypothesis space H, and we choose to learn from dataset D. The dataset D can be divided by, for example, 3 subsets. The subset for training, the subset for evaluation, and the subset for tests. Okay, then for algorithm, some example, X training example X and T, we choose to calculate the activation Z and update the weighted theta based in the error. The error is economic function or loss function that is common in the model of optimization for neural network. For example, this error might be last square error, might be order. There is a lot can be used in deep learning. Okay, for example here, h theta xe, h theta, it is for the model. Okay, h theta for the model predicts, but y a, it is the real in data set. When we have the loss function that we set to minimize, maybe we can use the sample method called gradient descent. This method has this iteration: theta t plus 1 equal theta t minus alpha learning rates theta delta theta, or the gradient of g theta. Okay, the alpha maybe can be optimized also in many articles. You can find it in our paper, where we add also the perturbation stochastic. For the case of regression, we can see my course that I teach in master in FPO for that, Khalid machine learning and Python. Okay. If we have more classes, then the output might be contain more neuron. For example, here, class 1, class 2, and class 3. And there is the technique that you can use for that, one hot encoding and softmax activation for last outputs here or layer. The question: what's happening if we have nonlinear data sets? Might be linear function, activation function, it's fail, or we have we don't have global solution because the problem is not convex, and the approximation also might be it is very far to the solution considered from the accuracy or loss function. Therefore, we need to talk about other activation function. Also, there is multi-layer perceptron for more approximation, the model of deep learning. This model have maybe the relation with differential equation in mathematics. Okay, problems or numerical analysis. Okay, then for multi-layer perceptron, they can be approximated with the continuous functionally arbitrary. For example, here we have the function from Rm to Rk, parameterized by the parameter here theta 1, theta 2, theta lambda for lambda layer. Okay, maybe our theta here can be the matrix or something more to such torch. It's called torch in the programmation modern. In each layer we have nonlinearity, then can be called G1 to G lambda. We start by the first layer Z1x equal G1 theta 1 x. Z2 might be G2 with theta 2 for Z1, etc. Okay. Here in general, or last one, Z lambda equal G lambda theta lambda Z lambda minus 1 of X. For the output, here we have arc max Z lambda of X. Then the probability for each, or the more probability largest for prediction which the object, for example, can be taken in classes. Then we can start by random initialization for the weights. We cannot start directly by the 0 because we have here a small random number and the derivative will be 0. Then it is slow. Then we can compute G theta and calculate the gradient of loss for update all parameters. For that, there is a technique, then I can use it also, it's called the backpropagation. Since we have for forward pass, Z, for example, if lambda equal to Z to X, here we have G2 and rho other like G1 multiplied, then it is a complex function. Also, there is other shows about the activation function, might be sigma weight and H Rouleau. In our work here, we talk about Hilbert Basis activation function, and theta is the parameter that we learned by iteration. That is the model, for example, fully connected neural network. The inputs, the first hidden, and the second, etc. The loss of function in general might be equal L Z for example, we have here lambda equal to, then Z equal to X, XE, YE, XE and E, it is coming in data sets. It is number of data sets, and here it is for the layer. The problem is how to compute the gradient of this function. Then by using the technique of backpropagation, we can start by outputs layer. The output layer, by using the partial differential, we have the value of the differential equation, and finally The theta can be updates by gradient descent. For sigmoid function, that is the form of the function, and here is the derivatives of sigma x. But there is some problems. For example, vanishing gradient or mark optimization be hard. There is also tangents hyperbolic and rective linear units that can give for all value inferior or less than 0, we have 0. Okay? Else max equal x. But it is also not differentiable in point 0. Okay, we can use softmax activation if we have more classes, and we can go to Hilbert Basis activation. This part for Hilbert activation basis, maybe we can use it the basic. We suppose that we have a number of Hilbert basic function, okay, then h e to x plus p, for example, basis. In this work, he of x might be alpha e parameters max 0 x minus beta e, with alpha e and beta e some real numbers. Okay, then for computation experiments, we suppose x and r in M, the input data matrix. Can do that for example, since we have the image, just to classify the image of minists and written number. The hidden layer of HPNN can be defined as flow h equal max 0 x multiplied by W1, the weighted matrix, plus B1 phi, okay, that is the matrix phi defined as flow, which components by using the Hilbert basic function, maybe which component of it can be computed. For last one, output layer, as we have here H, W2, the matrix connected, and B2, it is the layer, or is number of output classes. For robust or analysis probability, we can use different random subsets for training data sets. and also we fixed loss function for 20 inputs in training, and this is the results for minutes datasets with Linet 5. For train loss, the mean is 0.26. Here 45. For standard deviation 0.34, and here 0.03, etc. Also, we compared the activation function such as rouleau with our Hilbert activation function with key equal 1, 2, 3, etc. And this is the results that we find. So for example here, all of there with attest accuracy is more than the value of accuracy test of rule. Validation also for case 1 and 2. The loss for this case, also we have here the loss training is minimal, but for the third one is not this result. Also it is plotted for training loss, train accuracy, validation loss, and validation accuracy. The reference for introduction, we used this paper, and for Hilbert network we used the second paper. Thank you very much for your attention.